Welcome everybody to the first seminar from the Theoretical Statistical Ecology Group series for 2022-2023. I'm delighted to introduce André Menezes to you all. André did his undergrad and master's in southern Brazil, right, André, in the state of Paraná, in statistics. And then he worked for a while to Murabi Data Science. And while he was working for Murabi Data Science, he teamed up with Professor Hélio Migon, and he worked on this Python package that he's going to introduce to us today. So he calls it Detection of Structural Change in Dynamic Linear Models, and the name of the package is pybats-detection. So he's going to tell us a little bit about what this methodology involves, and a little bit about what the package can do for you and how we can apply it to ecology. So I thought it was really interesting. That's why we invited André to give this talk. Now André is researching for his PhD in the SFI Center for Research Training for Data Science in the Hamilton Institute at Maynooth University. So André, it's a pleasure to have you. The floor is yours. Thank you very much.
Thank you, Rafael, for the opportunity and for the introduction. So today the title of the presentation is, can you hear me okay, everyone? Okay.
Yeah, perfectly.
So today the title of the presentation is Detection of Structural Change in Dynamic Linear Models, the pybats-detection package. This is a joint work that I've done with Eduardo Gabriel and Professor Hélio Migon while working for the Murabi Data Science. And basically, I will give an introduction about what the context that I'm working, the model, and then I will give a brief overview of what is Bayesian dynamic linear models. And in the second, I will introduce you an idea of automatic monitoring for this class of model, the Bayesian dynamic linear models. And then I give you a brief overview of what a specific class of the pybats-detection package works. And I will finish the presentation with a simulated example showing the potentiality of one of the class of the pybats-detection package. So the takeaway message here is that pybats-detection is a Python package developed for Bayesian monitoring and intervention in univariate time series data. So I will emphasize monitoring and Bayesian here, especially in this talk today, I will talk more about monitoring, but intervention is also implemented in pybats-detection. This is developed by me and Eduardo Gabriel, one of my friends that I made during the master degree. And this work was developed when I working for a data science consult company called Murabi Data Science, and we were advised by Professor Hélio Migon, who is one of the great professors in statistics, especially in this area of Bayesian statistics in Brazil. The package is available in this GitHub repository and is also available in the Python index package, also known as PyPy. So the introduction, I need to give some reference about the background and what we use to implement the theory behind our package. So the package is specifically for a class of model that was introduced in the 1970s and was consolidated in this paper in 1976 by Jeff Harrison and Stevens, where the authors introduced the Bayesian dynamic linear model using ideas of Kalman filter and Bayesian statistics, Bayesian inference. This paper was very interesting at the time because especially in the field of statistics, nobody knows, in that time, people didn't know a lot of Kalman filter, and the authors introduced an idea of using Kalman filter with statistics. Kalman filter is an algorithm proposed in the field of engineering. During that time, Jeff Harrison, who was a professor in Warwick University, and other collaborators developed different extensions of this model and methods, and the theoretical developers were consolidating the book by Mike West and Jeff Harrison in 1997. The name of the book is Bayesian Dynamic Models, Bayesian Forecasts. And the two major works during this period was a paper by West and Harrison in 1986, where the authors introduced the automatic monitoring and adaptation in the class of the dynamic linear models. And in 1998, the authors introduced the Bayesian subjective intervention. In this talk, I will explore the ideas that was introduced in 1986 in this paper of Mike West and Jeff Harrison, and how we implement this. First, I will give a brief overview of the dynamic models, the ideas behind the paper, and how it is implemented in the pybats-detection package. So one of the things important when we are working with time series model is detect change and try to adaptate our model when this change is detected. So when I'm talking about change, I'm talking about structural change in the model. And so the question is, what is structural change? Structural change is a very simple definition, is when the time series abruptly changes at a point in time. And this could happen because, for example, changes in the location of the process, like in this first image here, the left, or changes in the scale of the process, which means the variance can increase or decrease over the time. And when in such case, the model should detect this change and should be adapted for this change in order to provide good forecast as well as for inference purpose. So here is we can clearly see some location change in the time series data for the simulated data, and here we can see increasing the variance from the 40 time, and also here in the 70th time we also see an increase in the variance. So in the context of ecological data, I did a very briefly search about what has been studying about structural change in ecological data, and I found this paper about this by this author and collaborators published recently, where the authors basically use a frequentist approach and assume that the time series can be modeled using some linear models. And to give a brief overview of this paper, the authors use a package in R called structured change. And in this package is some methods about how you can evaluate, how can you test hypothesis of structural change under a frequentist paradigm. And study of ecological indicators over time, structural changes can happen, for example, in the ecological data for ecological indicators such as species abundance, reproduction success, or species density or biomass. And as I said, when it should be very important and fundamental detect the structural changes or even outliers in order to improve first the forecast, as well as for inference purpose, to understand what happened in the past is also important to know. So now I will give a brief overview what's the Bayesian dynamic linear model, and then I will introduce the ideas of automatic monitoring that was in that first paper in the background of this slide. So Bayesian dynamic linear models are a natural extension of linear regression or linear models. That's because it's linear model here. And the difference is that the model is dynamic in the parameters that can vary along the time. So the model has go further to the well-known Kalman filter that was proposed in the context of engineering, and especially in the control theory. And it's based on the Bayes theorem. That's because it's Bayesian dynamic linear model. And one interesting property of this model is that it takes account the sequential nature of the data. I think it will be more clear in the next slide when I talk about inference aspects. That's the model. The model is defined by two following equations: the observational equation, where relates the random variable at time t with an unknown parameter and a vector of known coefficients or, sorry, known constants or regressors at time t. And we assume that we have a noise term here that we assume is normal distribution, or depends on the case, we can assume that it's a t-student distribution if the variance is unknown. And that's the variance of the observational equation. Here we have the state or evolution equation. This kind of representation of the model is also known in the literature as space states model. That's because we have two equations to describe this model. And the theta evolve over time according to the matrix G here, which is also known and can vary along the time, but it's not usually in the case in the models that I will talk. So the point here is that we have a covariance matrix for the parameters, variance covariance matrix for parameters for each time. So that's the definition of the model. And here, one important thing to mention here is that if we know the vector that relates the parameter with the observed data, and we know that the variance matrix G refers as station evolution matrix, and all the variance, the observational variance and the state space variance for each time, you can describe the class of dynamic linear models. The problem under an inference perspective that we do not know the variance of observational as well as the variance of the parameter, of the states parameters. And that's where the Bayesian approach will be used to estimate, to make inference about these two variance and consequently about the model. Here's just a particular and very useful model in the class of dynamic linear model known as linear or second order polynomial, linear growth or second order polynomial model. If we define f at time t be just 1 and 0, and G, this matrix here, we obtain the model that can be written in a form of system linear equation given by this expression, this system equation here. Here we have that the noise vector that I represented in the last slide by omega is decomposed into noise, one for the level, which is the mean, the me, and the other for the beta, that's the noise for the beta. This kind of model is very interesting, and the authors use Jeff Harrison specifically, and the students use a lot of this kind of model. I forgot to mention, but Harrison comes from he works for a textile industry and use a lot of this kind of work of model to provide forecast demands in a very online and sequential manner. So this kind of model is suitable for medium-term forecasts where the time series has some trend patterns. About the inference aspect, I will not give much details, but I will just introduce the idea of the inference. I'm talking about Bayesian inference here, and there are two major stages or steps involving the sequential inference. The first one is the evolution, and the second one is the updating. Basically, I have here my posterior distribution for my theta at time t minus 1, given all the information that I have in t minus 1, and I have to evolve this information for a prior distribution for my new theta at time t, given all the information that I have in time t minus 1. And with this prior distribution, I will obtain a forecast or a predictive distribution for my unobserved times data point at time t. That's the predictive or forecast distribution. And since I'm using a Bayesian I'm not, but the authors use the Bayesian paradigm, we can obtain all these distributions, all the inference here is made using probability distribution, not just point or interval estimates or confidence, depends. And then when we can, and this step here is important just for people that would like to know more about this model. This step here is interesting because here is where we use, here the update is where the authors use the common field algorithm to update my prior distribution at time t-1 to the posterior distribution at time t when a new data comes available. So the difference here for example, autoregressive models or the Box-Jenkins methodology is that we are working sequentially, which means that I do not need to re-estimate the model parameters when the new data becomes available. This procedure is made sequentially, which is very attractive when we are working online, or for example, if you are working in a company that needs, or if you are monitoring an indicator in an online manner. It's also important to mention here that all these calculations to obtain the posterior, the predictive, and as well as the prior distribution are obtained using simple, I would say, probability results about, since we are assuming normal distribution. And further details can be found in the book of West and Harrison. So now I will talk about the automatic monitoring proposed in 1986 by West and Harrison. And the main steps are, first, we need to define a measure to compare the model. Since we are working, here's important to mention that I have a current model, a model that I stipulated, and then I will check if this model has some breakdowns about the assumption that I made. To check this, I need to define a statistical measure to do that. And the statistical measure under the Bayesian paradigm, or is called as local base factor. The second one, I need to create or specify an alternative model for some potential change that I'm looking in a sequentially manner, and which means that I need to specify a alternative DLM, for example, to describe potentially structural change in the level or in scale or in the scale. And then I need to define, after detect this potential outlier, potential structural change, I will need to define what can I do in order to model recovery or to adaptate for this potential change. So define the subjective and automatic interventions. It's important to mention and to emphasize here that the method assesses the model performance. I will check or evaluate the model performance based on purely statistical measures. That's the base factor, which is an interesting property also. So what is the local base factor? The local base factor is basically a ratio of two predictive density distributions. Here in the numerator, I have the predictive density for my one step ahead. I think it's important to remember here that I'm working always with the one step ahead predictive distribution, which means that I'm not observing the true value of y. That's pretty different, for example, from usual time series data, especially in the Box-Jenkins context. So this is the definition of the base factor. I have the predictive distribution under the current model, and here in the denominator I have my alternative model. Here is important to note, since this is a ratio, if the two models, I mean the current model and the alternative model, are equal, which means that I don't have departures or I don't have any any potential detection against my model, my current model, then this ratio will be equal 1. However, if, for example, if my alternative model has a greater predictive distribution value evaluated at this time here, then I have a potential change, or the automatic monitor will sign something that's wrong with your current model. And here, so one point that it's implicit here is that the threshold. Which threshold are you use to define if the current model is worse than the alternative model? And we can generalize these local base factors, since we are working with time, for different times, for using, for example, the most key recent observations to compute this local base factor. Another two important quantities that are using the automatic monitoring is the cumulative base factor, which will, and this rule length. Both of these quantities are giving evidence against M0. It's like a way to monitoring the model using statistical measure or statistical paradigm. I will not explain better this, but it's, if you have any doubt, you can, any question you can answer, you can, yeah. So here, if you notice in the local base factor, I define the local base factor for my observation, or the response variable. However, it's very useful when it's the same, you work with the one step ahead standardized forecast error. And under the assumptions that we assume this standardized error has a standard normal distribution. And then the local base factor for a current model is basically proportional to this, because it's proportional to the density function of a normal distribution. And then we need to specify what is the alternative model, for example, for location in this case. For location, a natural alternative is just to think that the location is not 0, which means that the mean is not 0, and then we have this local base factor is proportional to this expression here. And then we compute the local base factor. Sorry, this is not the local base factor, this is the predictive standard. The local base factor is the ratio between these two here. And the local base factor is basically this expression here. Okay. So as I mentioned before, the sensitivity of the monitor will depend on the threshold that I will specify to compare the two models, this threshold tau here, below which the predictive error must be incompatible with the current model. The shift, we need to specify a value for this shift mean, the age, and also the maximum number of tamers to be considered in the cumulative, in the base factor a long time. Okay. And I will not have time to explore how to specify these models, but basically the recommended values according to the authors, and it's also, we can also prove this mathematically, are the 3 for the max, the L max, for the age are 4, and for the tau is 0.135. These two values, it's very easy to show what are these two values recommended, because since this value lead to indifference between M0 and M1 when the error is near to 2. Basically, the idea, to illustrate the idea here, I have my predictive distribution here for M0, and I have my predictive distribution for M1 with location weight. And I would like to, I'm comparing these two distributions based on the error standard, based on the local base factor. So I need to find this threshold here in order to when the error is near to 0. that's because tau is 0.135 and so on. There is a mathematical explanation for that. So here's how I talked in the last slides how we can detect the structural change and also potential outlier. But after that, what we can, what the method does. The method basically does the following. That's the rule that the method follows. I'm comparing if the age here should be B, but that's the local base factor is greater than tau. If it's yes, then I will check if there is some evidence, if there is some cumulated evidence against my model. I mean cumulated evidence because I'm looking for the cumulative base factor in the wrong lane. If this is okay, then the model is okay, then I go to the update step. For example, if my local base factor is lesser than the threshold that I specified, then this is a potential outlier, and I will reject my next observation and increase a parameter here that I didn't mention, but it relates to the uncertain of the state parameters. This parameter is known as discount factor. Discount factor is a concept of how the authors propose estimate the W variance in the state evolution equation. So what I'm doing here is basically decreasing this value to a very lower value in order to increasing my parameter uncertainty. Okay, that's basically the idea, and that's what I and Eduardo implement in the pybats-detection package. So now I will give a brief overview how the package is implemented and what are the main functionalities of the package. So the package is built under object-oriented programming, since Python has this feature, and we use Python classes. And the three main classes of the package are the smoothing, the intervention, and the monitoring. I will not talk about smoothing and intervention. I will just talk about monitoring. Okay, but if you have questions, I can try to answer. But basically, another important thing about the package is that the class depends on another package that was developed by these authors, that the package name is called pybats. Lavigne was a student from Mike West, and he and Cron introduced this package recently in 2021. And then we used the functionality of this package, more precisely one class, this class here. I don't know if you are familiar with class and oriented object programming, but okay. And then we use this class here, which is how we define a dynamic linear model. And basically we have to introduce a prior for my state parameters, a mean prior for my state parameter, a covariance prior for my state parameters, and then there are other arguments that specify the kind of model that you would like to use. Okay, and then that's our implementation. That's for the monitoring class. So an instance of monitoring class can be initialized as follows. We just imported the monitoring class, the object, and then they have the following arguments. The main argument here is the mod. The mod comes from an object of the class pybats-detection, sorry. And then the fit model and then we use a fit model. We try to follow I don't know if you are familiar with scikit-learn, but scikit-learn we initialize a class and then you have the fit and predict and so on. So we try to more or less follow this rule. Then we have, and then you can use the fit method to perform the sequential learning using the automatic monitoring concepts that I described in the last section slide. Okay, so the main arguments here are some default arguments here. You can, for example, try different kinds of alternative models, just specifying scaling instead of location. You can change the discount factor, which is a way where we can increase the parameters uncertain for different model components, for example, for the trend, for the seasonality, for regressors. And these are the default values that I presented initially. Okay. So you can find further details about the package through the vignettes, the quick start, and the pybats-detection, which is a detailed explanation about the usability. And now, going to the end of the presentation, I will just give a simple example, illustrative example, simulate some data sets. The simulated data set is generated from a normal generation process with variance is equal to 0.5 square, and we have different means over time. For the first 40 observations, I'm assuming that the mean is equal 100, and for the following 30, I'm assuming the mean is 104, and then the mean goes down to 98. So here basically is we would like to see if the monitoring package, and we can think that this as being a ecological indicator, for example. We can assume a normal, I'm not sure, I'm not from the area, but we can think that some ecological indicator would like to monitor some ecological indicator, and you know that some potentially outlier or potentially structural or changing the level of the circuit can happen. That's a bit of justification for this method in the context of ecological data. So the model we use is a simple level model, just one parameter, and from the definition that I gave in the beginning, if you take f and g just equal 1, we have this simple random walk model. It's very common model, very well-known model in the context of time series. And here's basically the code that I use to make inference about this data using the automatic monitoring and the monitoring class of our package. Basically, I define my prior and my prior mean, my prior variance, and then I initialize a class, and using the same code that I showed before. Basically, what the monitoring did was identifying some potential outlier at time 41, time 42, and time 43, and so on. That's basically, we need just 3 points to prove that this is in fact a level change in the time series data. Okay, so here is a graphical comparison of the monitoring of the one step ahead forecast mean and 95% credibility intervals using the monitoring, which is in blue, and without using the monitoring, which is in red. We can see clear that the monitoring with just 3 observations adaptate very quickly for the structural level change that happens in those 2 times here. So maybe you can think, yeah, that's the result I would like to show you. That's comparison. So just some concluding remarks. Just remember that the pybats-detection can provide the method for identifying structural changes and outliers in the class of Bayesian dynamic linear models. This methodology is very scalable and efficient for analyzing real-time series data. That's we use in when I was working for the consult for Morabey, we use a lot of this kind of technique because we have to analyze in an efficient manner and very online. I mean, yeah. And we have some plans to extend the intervention that I couldn't talk here, but also the monitoring for other classes of dynamic models, such as transfer functions. This particular kind of model here is the dynamic generalized linear models, which has Poisson, for example, and binomial time series data in this class of models. And this is another class of models called dynamic generalized exponential growth models. Okay, so that's it. Some reference here that's the one of the first paper of Harrison Stevens. And thank you very much.